Hello everyone, I'm David, and I'm here on behalf of the machine learning team at Ruter, and I will talk about how we at Ruter put the machine learning model into production. So I guess most of you know already who we are, who Ruter is, and what we do. But for those of you who don't, Ruter is the public transportation authority in Oslo and former Akershus, so the surrounding area. It was established in 2008, and every day we operate and serve around 4,800 stops and transport around 1 million people. So within Ruter, we have a data science department, and this data science department consists of two different teams. One team is the data warehouse team, and that team is responsible for curating and making available historical data. And this data is mainly used by the analysis department, and now more recently also the machine learning team. And the other team in the data science department is the team that I'm part of, the machine learning team. Our task is to improve the customer experience and make internal processes more efficient by using machine learning and artificial intelligence more generally. One example of what we do is that we have an AI bot that uses a machine learning model, an NLP model, that's been trained to classify customer complaints, and we use that to automatically reply to some kinds of customer complaints. But this model is not the focus of today's talk. Today's talk is about how we put a different model into production. And that model is our model for predicting passenger numbers. So this project started during COVID, and we wanted to answer the question, how full will the bus be? Because if we could answer that question, we could give that information to our customers, and then they could make more informed decisions about what bus to take and what routes to take in order to maintain social distancing regulations. But in order to answer this question, we first need to answer the second question here on this slide, and that is, how full was the bus? How full has the bus historically been? Now, the machine learning team can then simply go to the data warehouse and get this data from there, but where does the data in the data warehouse come from? Well, you may not have noticed, but there are actually sensors placed mainly above the doors in buses that count number of passengers that board and get off the bus at all stops. So this means that from this data, we're able to calculate how many people were on the bus at any given time, with some uncertainty, of course. So now we have data for how many people has been on the bus historically, and we want to predict how many people will be on the bus in the future. And to do that, we use machine learning. We've trained an XGBoost model to predict future passenger numbers. And the features that we feed into this model are mainly historical features, that is, what the passenger numbers have been in the past. So to predict the passenger numbers for a given departure, we look at and use as feature the passenger numbers on the same departure 1 week ago, 2 weeks ago, etc., and the average passenger numbers on that departure within the same hour 1 week ago, 2 weeks ago, etc. In addition to that, we have some time features, like what type of day it is. It is a weekday, is it a Saturday, or is it a Sunday? And what time of day it is. We train this model every day. The reason for that is that this model was developed during COVID and during rapidly changing and frequently changing regulations on social distancing and advice on taking public transportation. So we needed a model that was able to quickly adapt to changes in passenger behavior. The end product from this model is the predicted passenger numbers that we publish on Kafka. And then once they're on Kafka, they're ready to be consumed by other teams and be integrated in their products. And that's almost all I will say technically about this model in this talk, because how we did the machine learning is not the topic of this talk. The topic is how we got this into production. But I will, before moving on, show you also that once we had developed this model, we checked, is it ready for production or not? So we evaluated, okay, what is the accuracy of this model? Well, we found that we have a root mean squared error of about 5 passengers. And what we do is we take the output from this model, which is say 25 passengers on a given departure, and we classify it, also taking into account the capacity on the bus that will travel on that route. And we can then classify if this bus will have few seats available, many seats available, standing room only, or if the bus will be completely full at capacity. The pie chart in the top right shows how often we predict the correct or wrong category. So you can see the vast majority of this diagram is covered by green, which is the 84% of the cases where we predict the correct capacity or used capacity of the bus. While the orange is where we're one category off, and the red is only 3% where we're off by more than one category. We also look at, what does the passenger number on a bus look like as it travels along its route. That's showed on the plot on the lower half of this slide. And you can see that for this particular route, the passenger number increases as the bus starts its route, and it reaches a maximum at about stop 12 or 13, and then it decreases again. The blue curve is our predicted passenger number. The purple one is the ground truth that we try to predict. The sort of dark blue-green horizontal line, that's the number of seats on the bus, and the orange one is the total capacity of the bus, including standing room. So what we found looking at this is that, okay, we think this model is ready for production. So what do we do then? Well, what we could do is we could hand this model over to someone else, a different team, an operations team, say. But that led to quite a lot of questions like, how will we transfer this model to this other team? How do we know what kind of version of the model is running at any given time? How can we easily maintain it if we continually have to hand it off? How can we monitor it properly? How can we make sure that the way out to production, if we want to make quick changes, is short? How do we make sure that the features used during training is the same as the features used during prediction, so we avoid training and prediction skew? So what we concluded from this was that we, as in the machine learning team, we wanted to take this model into production ourselves. But how do we do that? Well, it's been a journey. We started simple as you can be, perhaps, where one of our team members trained the model on his laptop and then uploaded this output CSV with predictions to a shared storage, and then other teams could pick it up from there. But this approach, it's not scalable, right? So we think we've now created a framework that's significantly more scalable, more robust, more flexible, more reproducible. But by no means it's not perfect, we're not done. So if you have any feedback or suggestions at the end of this talk, we'd love to hear it. So the machine learning team, we decided, as I said, to handle the entire model lifecycle. We'll do the feature engineering and the model training, of course, but we'll also deploy it, we'll monitor it, we'll update it, and we will also retire it when the time comes. This does involve that the team needs more than just a core machine learning competence. We need to know as a team how to create CI pipelines. We need to know how to write infrastructure as code. We need to know how to operate an AWS account. So this, I'm sure to many of you, sounds like what a traditional DevOps team does, right? Most of you are, I'm sure, very familiar with DevOps. It's a methodology to deliver applications and services at high velocity, where one team manages the entire application lifecycle, where you go from creating and planning to verification, packaging, releasing, and monitoring, and then back to planning, all handled within one team. To do this, to facilitate this, these teams often use tools for CI or continuous integration that I mentioned on the previous slide, for automatic testing and automatic deployment, for example. And they also frequently use tools for infrastructure as code. So this methodology has been very successful for traditional development teams. But how do we transfer this to machine learning applications? And this is where machine learning operations, or MLOps, come into place, where we, in addition to all the things that the traditional DevOps team has to worry about with development and monitoring and all of that, we also have to take care of the machine learning part that's unique to a machine learning project. Because now we have a machine learning model that's been trained on data, and it receives data and produces predictions. So we need to make sure that this model that we have is reproducible. We need to make sure that we can reproduce the predictions we've made if we need to investigate why a particular prediction was made. During development, we need some kind of experiment tracking to make sure that we have a nice overview of what experiments we've already been running, which ones we want to run, and what the outcome was of those experiments. Maybe we want a model registry to keep track of all the sort of approved models that we've trained and all the metadata surrounding those models. We need to make sure that we can monitor both the model and the data to make sure that it always stays up to date, even though, because we know that data, real data, changes with time. And we need to be able to do continuous training when needed. So to do this, we use the Amazon SageMaker framework available on AWS. So Ruter is already on AWS. And the machine learning team is a small team. We don't want to use time on managing infrastructure, which means we want to use managed services as much as possible. And SageMaker is a fully managed service. And it has all the components we need. It has components for pipelines, model registry, feature store, experiment tracking, model training, data processing. It has Jupyter notebooks, and it also has integrated monitoring. So SageMaker is fully managed, but that also means that we have vendor lock-in. So that's sort of the downside here, that we are sort of locked into this framework now. And if we want to move to something else like Kubeflow, it would require some work on our side. To administrate our machine learning pipelines, we then use the pipeline component of this framework called SageMaker Pipelines. We show you the pipeline we have for the passenger count prediction on the right. And here you can see the very first step is a feature engineering step, which feeds into a model training step. And then, ignoring what's on the right, we see we have a publishing step where we publish our predictions to Kafka. And then we have a monitoring step where we monitor our predictions. And I'll come back to this step a bit later on. Each execution of this pipeline is stored And we can go back and see which executions we've done historically. If we go and look at one particular execution, we can here see all the parameters that fed into this model. We see the target date, that is the first date we wanted to make a prediction for. We have the DB sync date time here, which is a reference to the particular data set that was used to train this model. So we can always go back and look at exactly what the data looked like to this model when it was trained. And we have a flag for whether or not to run the monitoring and so on. And these pipelines, they can be triggered both in the UI and triggered on a schedule or programmatically. And each execution is reproducible. Right, so the pipeline that we've now created, we needed to monitor it. So what we've done is we have integrated the pipeline with Slack so that we will know if the pipeline fails or if an error message is produced during execution, but the pipeline doesn't fail, or maybe the pipeline doesn't run at all. Then a message will be posted on our Slack channel and we can start taking action. And then we usually reply to this Slack message like this to let other team members know that someone is on the case. So what tooling do we use to build our pipeline? Well, each step in our pipeline is usually a containerized Python application. We version these containers using semantic versioning, and we keep code that's common to multiple projects, multiple containers, for example, to do with logging in AWS Code Artifact, which is basically our own PyPy repository on AWS, so we don't have to duplicate that code. For continuous integration, we use GitLab CI, and you can see a screenshot here on the lower left of our CI pipeline for a containerized Python application. And you can see here we have a test stage with unit tests, and then we have a package stage that packages this application into a container. When it comes to infrastructure, we declare our infrastructure through Terraform as infrastructure as code. And we deploy this infrastructure in 3 different interacting environments. When I say interacting, I mean that this infrastructure that we deployed, it's interacting with other teams' infrastructure in Ruter. We also had the possibility to fire up development infrastructure on demand if we want to test out a new feature or make a change to the model and see what happens. And this is really valuable. We can do this without actually disturbing any of the live environments that we have. And our Terraform code is also integrated with GitLab CI, so we run Terraform plan and apply in GitLab CI. And we do not only monitor the pipeline and make sure it runs, we also monitor the data it produces. So I mentioned we have this monitoring step in our pipeline. What this step does is that it combines the predictions we make with the historical passenger numbers that continually become available as time goes by. So doing that, we have a dashboard that we created in Amazon QuickSight, which is a Power BI tool that lets us get an overview and insight into how well our model is doing on new data. The advantage of using a sort of a business insights tool like this is that we can dig down into the details of our predictions. So here is like the landing page, the overview, where you can see that we have a residual of about 5.24. And also that, our performance quality overall is good. As I mentioned in the previous slide, you can probably recognize this pie chart here. Now it's, I think, 86% of all the predictions we make are in the right category. We can also drill down and see how well we do on a particular journey, on a particular bus. And here we can see for this particular bus, we did quite well. We have some small deviations in the middle here, but overall, yeah, results are good. And for almost all of the time, we predict the right category. So this is good. But we do get a notification if the accuracy of the model depreciates beyond some threshold. So all of this is well and good, but we do still have some pain points. As I said, we have this training and prediction in the same step. It has worked well for us so far, but it's something we'd like to improve on. Certainly in other projects, we won't have this, so we need to generalize our framework. And also now that the world is hopefully more stable, we won't have to train every day. We also find that where things fail for us is often at the integration step. And for now, we only have manual integration tests, or end-to-end tests. So adding automatic integration tests would be a very nice thing. We also would like to provide a better experience for model development and feature engineering, where people usually work in Jupyter notebooks. We haven't really integrated Jupyter notebooks in our workflow. And that's basically because we haven't really worked on significant model development for a while. We've been very focused on building a robust framework that can support a model in production that we're comfortable and confident in. And we probably have many other things that will come up with time as we start taking this model further. But we have learned a few things on the way that I'd like to end with. It takes time and resources to establish an ML framework. It's taken some time for us. It's taken a bit more than a year to get to what you now saw. We're not a big team, and the team has needed and still needs a wide range of competence, ranging from Terraform and continuous integration tooling to data engineering and machine learning. But we think it's worth it. We also think that it has benefited us taking advantage of managed cloud services, because Ruter as an organization didn't really have the infrastructure that we needed centrally. Your experience may differ here. So yeah, that was the end of my talk. If you have any questions or suggestions, I would love to hear them. Thank you.